on Wednesday. So last Wednesday, or 2 days ago, we talked about derivations for non-integral powers of power series. So in addition, we talked about finding rescalings, right? So finding rescalings for singular problems, okay? And you could essentially do this systematically or by matching terms. Systematically just meant, you would go through all the orders that you could possibly use for your rescaling of x, right? X equals delta epsilon times some big X. And then you solve the problem for big X. In practice, if you don't have a lengthy problem, if you just have 4 terms or something like that, term matching can often work best, and just say I want to make these 2 terms of the same order in my problem. For non-integral powers, we talked about sort of identifying features of the problem that might clue you in to the non-integral power that you might have to use, okay? So double roots, right, of quadratics, okay? If you're expanding around those, this implies that you might have to expand in something like epsilon to the 1/2, right? For other algebraic problems, maybe of higher order, you may have other fractional powers that you have to expand in, okay? But in order to sort of find the expansion, you can just plug in something like x equals x0 plus delta 1 of epsilon x1, and essentially, again, match terms, right? So leave the fractional epsilon power ambiguous, and then see what happens when you make that expansion, and then choose it so that you get sensible equations in your hierarchy, and that the dominant terms are sort of getting canceled out as need be. This will you'll always have situations where you have to make a choice, right? And so you'll find that these asymptotic expansions, sometimes you have to do 1 or 2 steps of trial and error before you get the right choice of epsilon. Okay, so I think that's most of what we talked about last time. Any questions about that before we move on? Okay, so of course, we've talked about the expansion method before and the iterative method. So let's just talk a little bit about the iterative method for non-integral power series. Okay, so, and in particular, we'll just keep building off our original example equation. So if you remember, this was, 1 minus epsilon multiplied by x squared minus 2x plus 1 equals 0. So we have that 0 root, and the epsilon goes to 0 limit. If we rewrite it as follows, x minus 1 squared equals epsilon x squared, okay? Then we can create the following map. So xn plus 1 is equal to 1 plus or minus epsilon to the 1/2 xn, right? And of course, there's other maps that you could create here. You could take a square root and then divide by epsilon, but that's probably not a good idea, right? You usually like the thing on the right-hand side here, to be, not that much bigger than the thing on the left. Okay, so each time you update this, you're really only going to get an epsilon to the 1/2 perturbation of your previous guess, right? Away from 1. So let's start with just a guess. Call it x0. And we'll take x0 to be 1. And so the nice thing about the iterative procedure is that then thereafter, we don't have a lot of choices to make, okay? We just plug in and expand. So let's take the positive roots, or I guess I should say the plus root. They're both positive here. And we get 1 plus epsilon 1/2 x0. This is just equal to 1 plus epsilon 1/2. Okay. So far, so good. This looks like what we got from our expansion method from before, and also just expanding the original sort of full solution. X2, right, is going to be epsilon to the 1/2 times 1 plus epsilon to the 1/2, which now if you work it out, you get 1 plus epsilon to the 1/2 plus epsilon. Okay, so everything just sort of passes through. Let's do one more term, and we get x3 equals 1 plus epsilon to the 1/2. Now times this, right, which is going to give us epsilon to the 1/2 plus epsilon to the 3/2. Okay, so you can really see where this pattern is going, and you could probably derive, a general formula for the full expansion, which would just be, the sum over epsilon to the 1/2 to the n, right? So that's using an iterative method. Okay. In general, the choice that you have to make with the iterative method is really what map to use, right? And you may pick the wrong map to start with. You may get sort of nonsensical divergent series. Go back and choose another map, right? And the idea, again, is that you want to make sure your right-hand side is not going to cause a blow up, basically, in your expansion. So anything that's going to, increase the size of your solution, right, is probably not a good choice of map in this case. Okay, so what did we learn about this? Okay, so as we said before, expansion may require some systematic matching, right? So you may have to go through your problem and figure out how to choose your fractional power that feeds into your perturbation expansion for rescaling or for non-integral power expansions, okay? And a point I'll make is that iterative procedure can be slower, okay, but does not assume expansion form, right? So in cases where you don't want to go to the trouble of tuning and matching, right, you can essentially just derive a map that will give you this iterative expansion. Try that and see what the iterative procedure gives back to you, right? And I think those practice problems on the homework where you end up having to do both should give you some insight into, the speed of both of those methods and the sort of choice points in each of those methods, right? Okay. Questions before we move on? All right. So let's switch topics. We've talked a lot about epsilon power series. Okay. There's many ways of building up term by term asymptotic or perturbation expansions. Okay. and they're not necessarily always powers in epsilon, okay? So let's consider the following transcendental equation. F of x equals x e to the minus x, and let's say that this equals epsilon, right? So a harmless enough looking equation, right? I mean, you can't solve it explicitly except using special functions, but let's look at, okay, what just an intersection method might give us. So you see here, if we just plot this function f of x, and then we plot epsilon, then you have these two crossing points here. And the smaller epsilon is, the more you're going to push this large root out towards infinity. The smaller epsilon is also, the more you're going to push this small root down towards 0. And so that tells you that you're probably going to need different flavors of expansion for either root, okay? And so in particular, the root near x equals 0, I'll say, is easy to approximate, okay? And we can look at why in a minute, okay? The other root, okay, it gets large as epsilon goes to 0, right? So this idea of building an expansion that starts with some small epsilon, right? And then you take, you know, some even smaller function of epsilon, that's probably not going to work here, right? For that root. And the expansion is not really obvious, right? What do we do for such a large root? Yeah, we could try something like starting at 1 over epsilon or something like that. But you should get clued into the fact that, well, maybe the terms are going to be sort of exponentially small rather than just algebraically small in your expansion, right? Or somehow transcendentally small. So we need to sort of worry about that as we think of building up this asymptotic expansion. So if the expansion to use is not obvious, what method should we use to derive the solution? What do you think?
Iterative?
Yeah, if I don't know what expansion to use, just try using the iterative procedure, because I don't have to know the expansion in order to start in on that method, okay? And so a couple observations, right, is that the x factor here varies slowly, right? But the e to the minus x is going to vary more rapidly, okay? So let's separate those two terms when we write out the form of our equation, right? E to the minus x equals epsilon over x, okay? I can rearrange this a bit further. E to the x equals x over epsilon. And then if I take logs, I get xn plus 1 equals log 1 over epsilon plus log of xn. Okay, I mean natural log when I write log. I won't write ln. Okay, so why is this a good expansion? Yeah, it's got this big term here, right? But that's a standalone term that does not involve xn, right? And the only thing that's happening to xn on the right-hand side each time is that you're taking a log of it, okay? So this implies that, you know, probably this is something like the first term in your expansion. And then this will be some successively smaller set of terms that you build up, okay? That makes this a useful choice for the iterative map, okay? So then based on this form that we have, this suggests that we should try log of 1 over epsilon as our first term in our expansion, okay? And then note that log of 1 over epsilon will be small, right? Even when epsilon's really small, if you take log of a log, you're sort of shrinking that down, okay? Let me put it in quotes though, because if I take epsilon to be, 10 to the minus 20 or something like that, this is not necessarily going to be, 0.001. It could still be, some integral term or something like that, but certainly smaller than log of 1 over epsilon. So yeah, what do we get? So we get log of 1 over epsilon plus log of 1 over epsilon. Okay. And so we get this interesting expansion now, okay, in recursive logs, right? So that's fine. That's a feasible expansion. So maybe each term in this expansion, you just take another log of a log, right? So let's see what happens if we go up another step, okay? In order to help with my shorthand, I'm just going to call this L1 and L2, so I don't have to keep writing, log of that and log of that, okay? So let's see what we get for x2. So I get, again, my L1 there, plus log of L1 plus L2, okay? Now, if I write this out a slightly different way, okay? Log of L1 of 1 plus L2 plus L1. I can find a way to separate this into sums, right? So now if I use law of logs, I'm going to have a term that I had before, L2, and then some other term which presumably is smaller, okay? So let's see how that works. So I get L1 plus log of L1, which is just going to be L2, okay? And then I'm going to get log of 1 plus L2 over L1. So let's Taylor expand that. And if I do, I get L2 over L1 minus L2 squared over 2L1 squared plus so on and so on, okay? So I'm going to Taylor expand log of 1 plus L2 over L1, okay? Now, usually what we want to do in this case, right, is just to keep, not all of the trailing terms. I could keep, 1 or 2 of these terms, okay, and plug that into the successive iterative map, okay. Let's keep the next 2 terms here, okay, and plug that into my map again, and then I'll be done at third order in this series, okay. So I get L1 plus log of L1 times 1 plus L2 over L1 plus L2 over L1 squared minus L2 squared over 2L1 cubed. Okay, so I sort of did the same thing as before and factored out that L1. So now again, I can get L1 plus L2, okay? Taylor expand again, and now I get something manageable, but certainly lengthier, L2 over L1 plus L2 over L1 squared minus L2 squared over 2L1 cubed minus a half L2 over L1 plus L2 over L1 squared, so on and so on squared, okay? So when the dust clears, we have the first 2 terms that we had before. The next term we have is L2 over L1, which is smaller than L2, plus minus L2 squared over 2 plus L2 over L1 squared plus L2 cubed over 3 minus 3/2 L2 squared over L1 cubed plus so on and so on, okay? So at this point, you should be saying, well, you know, I don't see how in the world I ever would have guessed this asymptotic expansion, okay? And you would be right. You know, it doesn't necessarily build up recursively like log of log of log of log, right? You see that at subsequent steps, actually you take log of 1 over epsilon and divide it by log of 1 over epsilon, right? That's your next term in the asymptotic expansion. So there's no sort of, you know, pattern detection that you could use in order to figure out this asymptotic expansion, which is why iterative method is so useful, okay, especially for these transcendental problems, okay, because this would be a hard expansion, okay, to guess. All right. And let me also remark that the log of 1 over epsilon term, okay, this thing that we were calling L2, right? So for a very small epsilon is needed for a good approximation, okay? What do I mean by that? I mean, like, even when epsilon equals 10 to the minus 9, right? Log of 1 over epsilon is roughly like 3 in that case, okay? So in general, for transcendental equations, the iterative procedure is usually going to be the best, okay? Algebraic equations, you can usually be safe to assume you have some sort of power series. Transcendental equations, you could have series in sines or cosines, logs, exponentials, many different ways of expanding. Sometimes power series work for transcendental problems, but not necessarily, especially when you have sort of a mixture of algebraic and transcendental terms. Okay.
Zach,
Yeah.
so I'm trying to reprocess this, so let me know if this kind of makes sense. So the idea is we do this iteration and continue to get nested logs until the term inside of the next nested log is small enough for which a Taylor series is sensible. And that's why we don't go above L2. We don't have like an
Well,
L3.
yeah, you couldn't have done a Taylor series for log of 1 over epsilon, right? Like you're saying, I guess that's not sensible, right? But at the next step, right, you can separate things out into, you know, log of 1 over epsilon, which you had before, and log of 1 plus something else, which is small, right? And once you get to the log of 1 plus something else, which is small phase, yeah, then you can use a Taylor series, right? So, yep, that's the idea. Okay. All right, let's talk about convergence, and then I'll round it off with an example or two to finish. Okay. So another advantage of iterative methods is that they allow something like a proof of convergence. So expansion methods do not allow convergence proofs, right? Because that's sort of, as Sage was asking at the beginning, right? You can look at your series if you have a power series and say, well, I know what the next term is, right? Maybe I could say that the series is going to convert, the error that I'm going to make is going to be on the order of, epsilon to the n, the next epsilon, but you don't know anything about the prefactor, and you don't know how the term matching is going to work sort of down the line, right? So it's not always quite as simple as the kind of things you would get from sort of typical straight Taylor series expansions, okay? So the iterative method is really more useful for proving that you're gonna converge to a root of your original problem, okay? So to get a sense of this, suppose that something I'll call x star, okay, is actually the root of x of f of x, right? Common way that you could write sort of a root finding problem. And then, yeah, let's say that we define this map, xn plus 1 equals f of xn, right? As we've done before, okay? Well, then x is equal to x star plus some delta, okay, is going to be updated, okay, as follows. F of x star plus delta is equal to, and now I can Taylor expand, x star plus f prime of x star times delta plus little o of delta, okay? Meaning stuff that's smaller in order than delta, okay? So, of course, this requires knowing that you're close to the root to begin with, but sort of assuming that you are close to the root, this says that you should, keep perturbing your solution until you get closer and closer, okay? So if delta is small, okay, the error decreases if f prime of x star has magnitude less than 1, okay? So this is sort of a good rule of thumb for how to choose your iterative map, right? Is the gradient of this, okay, around where you are, because you're not going to know what the root is, right? But you can assume maybe you're close to the root. Is this gradient less than 1, meaning that you're sort of shrinking the perturbation that you add on to your expansion each time you run your iterative map, okay? So essentially by the contraction mapping principle, then x is going to go to x star through your iterative procedure, okay, if f prime of x star is less than 1 and delta is small enough, okay? Hand wavy proof, but that's the idea, right? That you can get convergence from these iterative procedures, but it depends on sort of choosing a good map. So for example, let's say that I had f was 1 minus epsilon x, right? And x star is somewhere around 1, okay? The root of my of the epsilon free equation. Therefore, f prime of x star, okay, is going to be roughly equal to minus 1 over 2 epsilon. That's small, okay? So that suggests that we'll get convergence, right? As long as I start close enough to the root and x star is presumably close to the root, okay? Another example, if we had 1 minus 1 over epsilon plus 1 over epsilon x star. Okay. Then if x star was approximately equal to minus 1 over epsilon, then f prime of x star would be roughly equal to minus, it would scale like minus epsilon. Again, that's small. It has magnitude less than 1. Okay. And we should expect convergence, right? All right. Let me yeah, a couple more examples. I'll skip that one. Let's go to a logarithmic example. So let's say f is equal to log of 1 over epsilon, log of x, right? Then x star is approximately equal to log of 1 over epsilon. Therefore, f prime of x star is going to scale like 1 over log of 1 over epsilon. If epsilon is small, then this is going to be big, so this is going to be small and close to 0. Okay, so again, we expect convergence. Okay, so the magnitude of f prime suggests, okay, the number of terms that are correct after n intervals, right? So if you sort of check the magnitude of f prime, okay, that's going to give you sort of the order of change that you should expect on that step of your iterative procedure. And the smaller and smaller this gets, the less and less your expansion is going to change, okay, from one step to the next. Okay. All right. So that's just a few words on convergence, but it tells you that even though iterative procedure can be a bit more work, right? You can say more about whether it's going to converge. It's easier to sort of check if it's going to work ahead of time and in the process. So in that regard, if you're clueless on how to proceed, go with the iterative procedure. Okay. Questions about this? All right. Okay. So we still got some time. So let me just give a couple more examples, right? Because I think that can help make this more concrete, especially going into working some of these yourself. So let's say, like, for instance, you have the following transcendental problem: x squared plus e to the epsilon x equals 5. Okay. Let's graph this. Okay. So if you're going to do this numerically, right, you might think, well, I could just I could plot this and then sort of look for where my roots are, and they're going to be somewhere like here and here. This is my e to the epsilon x. It's going to grow slowly if epsilon is small. Okay. Now, I don't know ahead of time what kind of expansion I might need to get. Okay. But it doesn't hurt to start with a power series, right? You can always try starting with a power series. If you go into the realm of trying to guess transcendental expansions, there's just too many options to choose from, right? But if you want to try and make the problem quick, you can try quickly guessing a power series. If that works, then great. Okay. So let's start with an expansion method. And let's say that I think that x is equal to x0 plus, and now I'm not going to specify what my power series is, but it's going to be something like e to the alpha x1, e to the 2 alpha x2, and so on. Okay. And then on the fly, we're going to choose what alpha is. Okay. So if I sub this in and expand, okay, then I get x0 squared plus 2x0, x1, epsilon to the alpha, plus so on and so on, plus now let's Taylor expand our exponential, 1 plus epsilon x0, plus so on and so on, equals 5. Okay. Now, I don't even really have to do much at epsilon to the 0, right? If I look at epsilon to the 0, I have this term, I have this term, I have this term, right? So I have x0 squared equals 4, x0 equals plus or minus 2, okay? In my plot, you can see that that's, roughly true, okay? Now, what I should see at next order, right, is that this term here needs a friend, okay? And so the only way to match it, right, without creating a term that's of smaller order that's unmatched, is to choose alpha equal to 1, okay? So I just have a nice regular perturbation expansion of this. If I chose an alpha that was smaller, this term would be unmatched, okay? And I would just have to zero out these terms, which maybe would work, but probably not, right? I'm probably just going to end up zeroing out a bunch of terms, okay? So usually I want to be able to pair up terms in the next order of my hierarchy, okay? So because I must match, right, epsilon to the x0 with 2x0, x1, epsilon to the alpha, then we're going to pick just alpha equals 1. Okay, so at epsilon to the 1, I get 2x0, x1 equals minus x0. This implies that x1 equals minus a half. And so x, so far, what I have is plus or minus 2, okay, minus epsilon over 2. Okay, maybe you only want to go up to linear order, okay, but we could go further if you want to. Okay, questions about that?
So in the last transcendental equation we looked at, one of the roots seemed to be growing, so it was a singular problem. But here, I think they won't be. So is that a good reason to expect that we would have a standard power series as opposed to?
Yeah, I mean, where you run into problems is, sort of pushing a root out towards infinity means that you can't do something like, just expand around, 0 or something finite, right? When the leading term is infinite, right? Then that's a clue that you may have to do something transcendental or with an iterative procedure. Also, the fact that you're not sort of coupling these terms together, right? They're separate. You can just immediately think of, well, what happens when I Taylor expand this? If you Taylor expand it, then you're really just working with an algebraic equation. It's just an algebraic equation with an infinite algebraic series, right? The other problem, right? You could do that, but the accuracy is it's going to be much harder to determine sort of out at infinity. Really, the issue there was your leading order term. Yeah. Okay. All right. So let's look at the iterative procedure for this, just for comparison. So let's say that I have I want to create a map. Okay. I can move this over to the other side and take a square root. So I can move the exponential over to the other side and take a square root, and I would get square root of 5 minus e to the epsilon xn, okay? And this is going to be for our positive root, right? I could have taken this to be negative, and then that would give me my negative root, okay? So often a good plan is then to just take the epsilon goes to 0 limit and use that as your first guess, right? So in that case, we know that x0 would be equal to just +2. Okay. So starting from that x0, I get x1 equals 5 minus e to the 2 epsilon. This, if I expand out my exponential, I get 4 minus 2 epsilon minus 2 epsilon squared. Okay, just Taylor expanding. Okay. And if I then further Taylor expand my square root, okay, I'm going to get minus, or use binomial series. I get 2 minus a quarter 2 epsilon plus 2 epsilon squared. Okay, other terms in there, but they're of higher order. Okay, and because I only want to really add on maybe one additional order of term each time. Okay, let's just say the next term is going to be just 2 minus epsilon over 2. Okay, and then I'll drop the other terms when I iterate. Okay. The next step would be x2. So we get e to the 2, 5 minus e to the 2 epsilon minus epsilon squared over 4. Okay, all within the square roots. Okay, Taylor expansion of the exponential. Okay, and then Taylor expansion of the square root, or epsilon over 2. Okay, plus some higher order terms. Okay, this is going to be equal to 2 minus a quarter 2 epsilon plus 7 epsilon squared over 4 minus 1 over 64 for epsilon squared plus higher order terms. So if I simplify down, I get 2 minus epsilon over 2. That's reassuring. The leading order terms are still the same, 2 minus epsilon over 2. And then my epsilon squared term is just going to be epsilon squared minus epsilon squared over 2. Okay. So you see that I get the same, first couple terms here, and then, I can create more terms. And we could, expand these out to higher order if we want, and just, check that they match in this case. Okay. So what's the point here, right? Here it was fine, you could sort of guess an expansion and it worked, right? Iterative procedure, the key is really just choosing this map, and then Taylor expanding sort of when it makes sense to do that, and just keeping sort of one extra term each time. Okay. All right. I got 3 minutes left now. I think I'll just maybe start this one. Okay. And it's another transcendental, right? Because these are usually the more questionable ones. So let's say that we have x plus 1 plus epsilon hyperbolic secant x over epsilon equals 0. What does this look like? Okay, so let's draw it out. This is epsilon hyperbolic secant of x over epsilon, looks like this. And then here is -1 minus x. Okay, so you have this intersection point here. It's close to x equals -1. Okay, and let's just forget about trying to do expansion method. You could try, but we'll just jump right into the iterative method. Okay. And so then the question is always, what's the best thing to do? Well, if you see here, if I just move these terms to the other side, right, I have something that's order 1 and then something that's order epsilon. So that may be a fine map to use, right? Because each time the perturbation to my series should be small, right, within here. So x0 to start with, well, this should be small, and then my leading order term is just -1. So let's start with that as a guess. X1 then is equal to -1 minus epsilon times 2 over e to the -1 over epsilon plus e to the 1 over epsilon. Okay. So the question is sort of how to deal with this. So if I look at this, right, e to the 1 over epsilon, right, that's going to be huge, right? It's going to be exponentially large. E to the -1 over epsilon, that's going to be exponentially small, really small, okay? So I could, I could do something like Taylor expansions, but I can just sort of drop this term here because it's going to be way, way, way smaller, okay, than the leading order term there, okay? And in general, there's not necessarily one path to deriving an asymptotic expansion. Dropping this term is sort of one way of doing it. If you didn't, then probably down the road in this step, you would end up dropping this term, okay? So knowing this, right, I can say, well, this is equal to -1 minus 2 epsilon. Drop this term, and then I just get an e to the -1 over epsilon plus things that are smaller, okay? So this now becomes my next term in the series, right? It's transcendental, right? So this might have been a hard thing to guess, okay? The next step then would be taking x2 to be -1 minus epsilon, and hyperbolic secant of 1 over epsilon times -1 minus 2 epsilon e to the -1 over epsilon, right? And I see that I'm over time. So I think rather than sort of rushing through this, I'll maybe lead off with this on Monday before we get into the rest. But yeah, if you want to try and go the rest of the way with this step over the weekend, be my guest. But we'll recap this at the beginning on Monday. So I'll pause there. Any questions about these approaches though?
Would it, so when I first saw this, I expected us to Taylor expand hyperbolic secant. Is there a reason that we would expect that not to work, or are you just trying to demonstrate?
Yeah. So again, it's this issue of this term that we get here. How do you even expand this, right? What do you expand it around, right? E to the -1 over epsilon is not going to have an easy sort of power series expansion. So you sort of have to keep it as a transcendental term in order to respect how transcendentally small this is. E to the -1 over epsilon is smaller than any power of epsilon, essentially, in the limit as epsilon goes to 0. So that's the problem with Taylor expanding it. Yeah. Okay. All right. So just to recap, so we kind of talked about really some of the virtues of the iterative method today. You can prove convergence. It works better for sort of transcendental equations involving logarithms. And we talked a little bit more about sort of how to handle building up these asymptotic series when they involve transcendental terms. On Monday, we'll just finish this example up and we'll talk about perturbed eigenvalue problems. And then we'll move to more of some of the mathematics of asymptotics, big O, little o notation, how to sort of use those with asymptotic series. And that's sort of moving into the second chapter of the Hinch book, if you're following along there. Okay. Well, if there's no other questions, have a good weekend, and I'll see you all on Monday.
Thanks, Zach.
Yeah, thanks.
Did did a bunch of people drop, or are we just missing a bunch of people today?